In this lecture, we're going to talk about a primitive whose job it is to produce keys for symmetric key primitives. This is something we've kind of swept under the rug. If you think about the PRF security notion or IND-CPA for encryption schemes, etc. And these security notions, they all begin by saying pick a key uniformly at random from the key set. And one can ask, where exactly do these uniformly sampled keys come from? And it's important, right? Because you can't say that a scheme achieves IND-CPA security. I mean, you can say it, but then if you actually try to implement this scheme in practice, and you can't guarantee that the keys that are being used are in fact uniform random bit strings, then the theoretical result doesn't really hold in practice. So this is an important piece of cryptography in the real world, this idea of how does one actually guarantee that they have symmetric keys that are uniformly random bit strings? Where does this entropy come from? Unless you are in a situation where you have a very restricted number of parties who are participating, it's really unlikely that you're actually going to be able to harvest enough entropy from physical processes to actually generate, thousands and thousands of uniformly random 128-bit strings to hand out to all of your users. Putting the key management issue aside, just the generation of this many number of random bits is hard. Harvesting entropy in reality is hard. So we're sort of forced to ask the question of, okay, what do we do in practice? In particular, we often will have these entropy sources. On some systems, this will be like the timing between packets arriving at your network interface, or movements of the mouse, time between key clicks, things like this are what we call entropy sources, but they're not likely to be uniform sources. They're likely to be highly non-uniform, in fact. If you think about your rate of typing, it's not the case that the time between keystrokes is going to be the same always. There's variety among them. So we have to figure out a way to take entropy that's harvested from these non-uniform sources and somehow turn it into a string that is a collection of uniformly random bits. Another quite common application of a key derivation function, which is the object whose job it is to do this processing of non-uniform bits and turning them into uniform bits. Another really important application is the one I've drawn here in this kind of magenta picture. So if you've got some client application, like a web browser, and it's connecting to a remote server with whom it doesn't share any randomness source. It doesn't share any kind of secret bits to start with. They carry out this exchange of messages, a protocol, whereby maybe the client app sends a message M1 to a remote server, and this message may contain entropy from the client side random number generator, say. But the remote server doesn't share this source of entropy. It may have its own source of entropy, and so it includes some randomness in its own return message M2. And more generally, there may be multiple rounds of messages that are passed, but each of them may contain some randomness from one side or the other, but the randomness sources are not shared. And at the end of this exchange of messages, this protocol, we want it to be the case that you can take the transcript of the messages that have been sent back and forth and run them through something called a key derivation function and have that output the same string at either side. And not only do we want the string to be the same so that they can use this now as a shared key to, in order to power symmetric encryption, we need it to be the case that in order to have the theoretical results about security for encryption schemes, in order for those to hold, we not only need this string to be the same at both sides, but we need this string to be indistinguishable from uniformly random bits. And in a very strong way, we actually need them to be as if they were a sample from the set of possible keys. This is precisely the job of a key derivation function. And one thing to notice is long before we actually get into formalizing what a KDF is to notice that because these two sides don't share the same entropy source, and yet they need to arrive at the same string, this function, this KDF, needs to be deterministic, right? Because I need to be the case that if you put the same inputs in on both sides, you get the same value out. And if the KDF itself were randomized or stateful, then you're not guaranteed that they get the same string out. So this is a deterministic function. It's taking in some kind of randomness from this side and some kind of randomness from this side and deriving the same key, and in such a way that this shared key is a string of bits that are uniformly random. This is a pretty tall ask, but this is precisely what KDFs do. Well, so before we can talk about KDFs and creating random bits, we really need to establish some formal description of randomness. We talk about random bits all the time, but for this lesson, we actually need to have some kind of formal basis of how we talk about randomness. Well, when we talk about randomness, people often will use the term entropy. And I don't want to assume that everybody here has a good grasp of entropy, and in particular of the different kinds of entropy that matter. So I'm going to actually introduce that first now before we can move on. So let's let capital X, and I'll try to use this serifed handwritten typeface for random variables. Let's let capital X be a random variable taking on some values little x that are in some set, calligraphic X. And the random variable takes on these values with the probability written in the usual way. But what this probability means is that there's some underlying distribution d sub x on this set. And we define the probability that the random variable takes this value by what's the probability that if I sampled once according to this distribution that I would actually get this value little x. That's how we define the probability of a random variable equaling x. Okay. I'm hoping that's mostly pretty familiar. The first thing I want to introduce is information. So the information that's transmitted by seeing a particular value. So you've got some randomized process that has some underlying distribution. And in the information theory world, we talk about how much information is conveyed by seeing a particular value of this random variable, by seeing a particular sample from this distribution. The information is measured by a function which maps elements of the underlying set cal x to a real number. And in particular, the information that is transmitted or that is gained upon seeing a particular value x is essentially the number of bits of surprise that there are. What do I mean by that? It's defined to be the log 2, so the number of bits of this quantity, 1 over the probability of actually observing that value little x. If that value is surprising, then that means the probability is quite small. You really didn't expect to see this value. So this number's small, which means 1 over it is big. So you can encode lots of bits into an unlikely value. So this is the amount of information that you can transmit or convey, or that is captured by seeing the value little x. And here, because 1 over, when it comes to logs, you just pull a minus out front. This is the typical way that you'll see the information of value little x being defined. Okay. Now, entropy. When most computer scientists think about entropy, what they are really thinking about is something called the Shannon entropy. And the Shannon entropy is in fact the average amount of information. So on average, if I sample from some underlying distribution, on average, how many bits of surprise, how many bits of information can I transmit? So the Shannon entropy is defined to be the over all possible values that the random variable can take, the information conveyed by that value, weighted by the probability that you actually see that value. So particularly, this is the expected value of the information of the random variable. This is the average information, or the Shannon entropy. And that's all well and good, except in cryptography, we're not often interested in averages. And in particular, in cryptography, we focus on another kind of entropy, which is called the minimum entropy, or the min entropy of the random variable. And before I talk about the definition of it, let me give you some intuition for it. Imagine that you are an adversary, and you're trying to guess a password. you have some underlying model, some distribution over passwords. Say that's been established by seeing lots of password breaches. So, you can find these things various places on the internet. If you look hard enough, you can find these password breach sets, which gives you the passwords of a bunch of users. If you took the histogram of all those passwords, you'd get an estimate of a distribution of how people choose passwords. For example, the password or password123 or ABC123. These are really common passwords. So those would be ones that if you were trying to log into a site using a guessed password, you probably would use one of those. And so indeed, if you only had one shot at guessing the password, which one would you guess? You'd guess the one that's most likely. So you'd pick the one that's the maximum over all possible values x, all possible passwords, the one that has the highest probability. This is exactly what min entropy captures. It's give me the most likely value, or from the security perspective, the worst case. It's the number of bits of surprise, or the number of bits in the most likely. So if you were to move this minus inside, it'd be 1 over this, right? So it's capturing how hard is it to guess the value of a random variable. That's what the min entropy captures. So it's a worst case from a security perspective. And because we're concerned about adversaries, we think about worst case guessability, or from the adversary's perspective, best case guessability. Average doesn't really help us. If there's lots of passwords, but most of them are really unlikely to be used, we don't really care that on average it's hard to guess. We care about, if you know the distribution, how hard is it to guess the most likely one? So min entropy is the thing that we are most interested in, not the Shannon or average entropy. From a more visual perspective, so here's a distribution in magenta. This is some meta distribution. This is the probability that the random variable takes on a particular value. So think of this as like the probability that the password is actually this. These are all the possible values of that random variable. So think of all possible passwords. This is my distribution over those. If you had to guess the outcome of an experiment that's going to sample from this distribution, you'd guess that this is the value that's going to occur. This is the maximum probability. So the maximum probability, if you look at it in terms of the min entropy, is 2 to the minus min entropy. That's just gotten by taking a minus to this side and then raising both sides to the 2. So the maximum probability of the distribution is 2 to the minus the min entropy. I point this out because I want to be clear that small min entropy is bad. Large min entropy is good. So in particular, if you have a distribution with small min entropy, it means it's easy to predict the value that's going to be output by sampling. So for comparison, let's say you have min entropy of 2 bits, we say, because it's log 2, yeah. If you say distribution has 2 bits of min entropy, and that means that the most likely outcome of sampling from it happens with probability 1/4. That's pretty easy to guess. 1/4 of the time you're going to be right just by guessing that value, and expectation anyway. If instead I say the min entropy is 80 bits, that means that the most likely value occurs with probability 1/2 to the 80. That's good because all the other values occur with probability at most that, probably less than that, and that's a very small number. So from a cryptographic perspective, what we want is a distribution with high min entropy, not low min entropy. Low min entropy means easy to guess, high min entropy means hard to guess. But I do want to point out that there is a relationship between the min entropy and the average entropy if x is indeed a uniform distribution over this. Then the min entropy is negative log of the most likely value, but all outcomes have the same probability, 1 over the size of the set. So the min entropy is log of the size of the set. Likewise, if you look at the average entropy, well, since everything has the same probability, then if you plug these in, you get exactly the same value. And this is what you'd expect, right? If you have a uniform distribution, then the most probable outcome is the same as the average outcome because everything has the same probability of occurring. All right. Well, it would be awesome if we had entropy sources in reality that gave us uniform bits as outputs, but these are extremely rare in reality. Like I said, typically systems end up harvesting randomness or harvesting entropy, as we say, by looking at the rate of key clicks, the inter-packet arrival time at the network card, the movements of your mouse, other things like this that are not very much not uniform. So if we had a uniform source, that'd be great, because then we could just say, give me 128 samples from this uniform source, and I can call that my key for AES, for example. We don't have those. In reality, what we have are distributions. We can harvest entropy from distributions that are non-uniform, but maybe we get some guarantee about the min entropy of them. In other words, we might not know anything about the shape of the distribution, but all we can guarantee is that the most likely value in the distribution is not too likely. Yeah, that's what we get in practice. And so in applied cryptography, what we're left with is this problem of, given that I can get random but not uniform bits, how do I turn those into a string of uniform bits? This is the job of the key derivation function. Okay. Well, this is a screenshot, a little snippet from a paper that I quite like. It doesn't do everything exactly the way I'd like to see it, but it's a nice paper, and it's sort of surprising that until fairly recently, so Crypto, which is one of the top, maybe the top conference in cryptography, it wasn't until 2010 that we get this paper that actually, in one place, formalizes what a key derivation function even is. It's such an important primitive in practice, and yet until this point we didn't really have a paper that described them carefully. So this is a snippet from that paper, and they're describing in this definition something called an extractor. And loosely speaking, the job of an extractor is to do what a key derivation function needs to do. That is, you provide me some kind of an input that's got some randomness in it. Not uniform, but some kind of randomness there. The job of an extractor is, as the name suggests, to extract from a potentially long string of non-uniform random bits, extract from that a almost certainly shorter string in which all of the bits are uniformly random or very close to uniformly random. This is an extractor, a randomness extractor, an entropy smoother. These are all names for the same kind of thing. We're just going to call an extractor. So here I've taken this snippet from that paper because it does a decent job of defining things, and I've scratched out some stuff to match the notation that we have. So let's read through this. So let's let d of x, this is the distribution we've been talking about, be a probability distribution over strings of length n. And here, I don't want you to think of n as being like a block size, 128. Just think of n as being some number kind of large. We've got some distribution, and we've got some function. So this is a deterministic mapping called ext, extractor. It's going to take in a t-bit string and an n-bit string. An n-bit string is going to be a sample from the distribution here. And it outputs a string of length m prime. We'll see where the prime comes from in a moment. This function is called a delta statistical extractor with respect to this particular distribution if you imagine the following game. Either I sample a t-bit string r. We're going to call this the seed. This is like seed randomness. It's kind of starting randomness for the extractor. You either get handed a pair, which is the seed for the extractor, and the output, y, of the extractor using that seed randomness and a sample from this distribution. So you get handed the seed and the output of the extractor when run on some non-uniform input. That's one possibility. The other possibility is you're handed the seed and a value z, which is actually a uniform string of the same length as y. You're handed one of these two, the seed and the extractor output, or the seed and a uniform string. And we say that the extractor is delta statistical with respect to that distribution if no distinguishing test, even computationally unbounded ones, can distinguish between these two possibilities with probability better than delta. So here, I've sort of pulled out this section here, try to say this again. So let's let A be any distinguishing algorithm, even a computationally unbounded one. Then this definition is saying the probability, the difference of probabilities of being handed either the seed and the extractor output or the seed and a uniform string the difference of any test outputting 1, so think of 1 as having the semantics of I have this kind of output. The ability to distinguish between these two possibilities is at most delta. Here this probability is over, as a reminder, the sampling of the seed randomness, sampling x from the starting distribution, and then running it through the extractor. This probability is over sampling of the seed randomness, and then a uniform sampling of a bit string of the same length as the extractor output. That's what it means to be a delta statistical extractor with respect to this particular distribution. But really, what we want is not something that works for a particular distribution. Because, in cryptography, we're all about trying to provide general purpose tools, so we don't have to be concerned about how users are going to use them. What we really want is something that works not just for a particular distribution, but we want this. We say that the extractor is a delta statistical extractor, period, if it satisfies this definition for all distributions over n-bit strings that have a guaranteed min entropy m. In that case, we say the extractor is m delta statistical. So that means you take this thing and you universally quantify it over all possible distributions dx. That's it. So you can see the relationship here between m and m prime. And this is going to be critical because what we're going to establish shortly is, in fact, the relationship between the various parameters, the amount of min entropy that's in the distribution, the size of the output of the extractor, the closeness of the extractor output to uniform, and the amount of seed entropy that goes in, the amount of seed randomness that goes in. I get that this is all pretty heavy stuff, particularly if you don't already have a background where you're used to thinking about entropy and this kind of stuff. So let me try to show this another way. This general purpose, this m delta statistical extractor, is giving us a way to take some string x, which is n bits long, and think of n as being kind of big, bigger than m prime for sure. We have some number of bits n, and within these bits, we're guaranteed that across all these bits, there's some amount of min entropy m, meaning no n-bit string occurs with probability better than 2 to the minus m. Okay? So of course, if this is a uniform string, you'd say the min entropy is n, but these aren't going to be uniform strings. So we've got this long string of bits, and we're guaranteed that this long string of bits won't occur with probability better than 2 to the minus m. We take that long string, and a little bit of actual seed randomness, seed entropy. So maybe we've spent some time really working hard to find a few uniform random bits as like a bootstrapping. We take that, this long string of non-uniform bits, and the extractor's job is to take these two and process them together in a way that we get an output y that's m prime bits long, but every one of the bits in this string is very close to uniform. And in particular, if you compared this string with a truly uniform string of bits of the same length, they'd be delta close to each other. Hopefully this multiple attempts to explain this makes some sense. If it doesn't, back up and listen to it again so you can unpack what an extractor is supposed to do. All right, let me move on a little bit. We've said multiple times in the last few minutes this thing of delta close to uniform. What exactly does this mean, delta close to uniform? Well, let's make it precise. Whenever you say something is delta close to uniform, what we're talking about is actually something called the statistical distance. So the statistical distance between a random variable x, whose distribution is this dx we were just talking about, and a uniform random variable on the same set. So in other words, how far away x is from uniform, in a sense, is defined to be this. And rather than looking at this, let's look at this picture for a moment. Here, the yellow line is the uniform distribution over the set. So every point here on this yellow line has the same probability, 1 over the size of the set. The magenta curve is the actual distribution of our random variable x. And the statistical distance is effectively defined to be, at every point, compare the probabilities between the magenta line and the yellow line. If they're the same, the distance between them is 0, but as soon as they start to differ, whether it be in the positive direction or in the negative direction, you can think of this as like contributing to the distance between these two distributions. That's exactly what this line is capturing here. It's saying take the sum over all possible values of x of the absolute value of the probability that the random variable that you care about takes on a particular value. So the magenta curve. The absolute value of that probability minus the probability that a uniform distribution takes on that value. So the distance at any point between these two curves, the magenta and the orangey yellow one. And you sum up over all possible values of x. So we're talking about all this shaded region here is the total area between these two things is the statistical distance when you scale it by a half for technical reasons. If we say something is delta close to uniform, well, of course we know the uniform distribution takes on every value with this probability 1 over x, so we just replace that here. To say that x, the random variable, is delta close to uniform is to say that this summation here, when scaled by 2, is at most delta. In other words, the area here, the shaded area, is at most delta divided by 2. All right, that's what it means to be delta close to uniform. Pause.